Hello everyone, and welcome back to the game you can win, but cannot play. I always have to say it like that, I guess. Anyway, today we're going to get right into it. We're going to talk about what topological games are, and we're going to start with the topological game that started it all, the Banach-Mazur game. Alright, so let's start with the basic question. What actually is a topological game? I've been hyping it up for, 3 videos now. What is it? Well, a topological game is a type of infinite positional game of perfect information. Alright, what is that? Well, to understand what a topological game is, I think it's probably easiest to talk about the sorts of games that mathematicians, especially pure mathematicians, really like thinking about. So I call these mathy games, and this isn't really a definition. These aren't hard and fast rules. These are just the general things that mathematicians like to talk about when they talk about games, or rather, the games that mathematicians like to talk about. So, a mathematically ideal game is one in which, first, there are 2 players, because that keeps things simple. Furthermore, this game is turn-based. Players should take turns, somehow influencing the state of, a board or a game state or something. Something that's more real-time, like, sports or fencing. Ha, ha, yeah, fencing, oh no. That's not something that's very easy to analyze mathematically. Furthermore, a game should be, if you want to analyze it super mathematically, it should be deterministic. That is, you should be able to know what the result of all your moves are. So tic-tac-toe, for instance, is a deterministic game because whenever a player makes a move, and they say, oh, I'm putting an X in this square, oh, so that's going to change things by making there be an X in that square. And by contrast, something that's a game that's not deterministic might be something like Yahtzee, where, if you make the move of roll the dice, you don't know what the result is going to be. That was 3, 2 4s, a 5, and a 6. Small straight. Anyway, games that we analyze mathematically should also be games of perfect information. That is, games where every aspect of the board state is known to both players. So in tic-tac-toe, for instance, both players know exactly what letters, or lack thereof, are in each square. Here there's an X in this square, an O in this square, no letters in any other square, and both players know this. By contrast, in a game like poker, each player has information that only they know, their hand, and no other players know, and they have to strategize around this. We don't want that. Finally, a game should be zero-sum in the sense that it is impossible to draw, it is impossible to tie. Either player 1 wins, or player 2 wins. Alright. So, why do mathematicians like their games to be like this? Well, the answer is, these games are ideal for making strategies for. Not just strategies where it's like, oh, if you play this way, you're more likely to win. Strategies that are like, oh, if you play this way, responding to your opponent's moves in this way, you are guaranteed to win, no matter what your opponent does. So to give an example of a game that has this sort of perfect strategy, let's just do the game of NIM, or subtraction as it's sometimes called. Other people use NIM to refer to another game, whatever, where we have, some number of game pieces, like that, and on each turn, a player takes either 1 or 2 of these pieces. So maybe player 1 goes, I'll take this one, and player 2 says, I'll take these 2, and so on. And then whoever takes the last thingamabobber that you're taking is the winner. So, what is the perfect strategy for this game? Well, if you're familiar with this game, you know that the perfect strategy is always make the number of doodads a multiple of 3. Because that way, say player 1 takes this, player 2 makes a multiple of 3 by taking these 2. Player 1 takes these 2, then you make a multiple of 3 by taking this one, player 2 does. Player 1 takes these two, player 2 takes these two, and now, no matter what player 1 does, because we're down to 3 here, player 2 will always be able to take the last one. If player 1 takes 1, you can take 2, and if player 1 takes 2, you can take the 1. So player 2, we say in this case, has a winning strategy. And note that which player has the winning strategy might depend on the exact setup of the game. So, for instance, if our game instead looked like this, with one extra doodad that we're trying to take, then rather than player 2 having the winning strategy, player 1 would have the winning strategy. Because player 1 could take 1 and leave player 2 with a multiple of 3 doodads. And then player 2 would have to take either 1 or 2, and that wouldn't be leaving player 1 with a multiple of 3. So, they're kind of sunk. Player 1 can always leave player 2 with a multiple of 3, eventually getting to this point where, it's a foregone conclusion that player 1 wins. So, what is a topological game, then? So a topological game, it follows all of these characteristics, but there are 2 more. The first extra criterion is that the board states involve topological spaces and sets in topological spaces. Alright, so this is a pretty normal requirement we might expect. I mean, it's a topological game, presumably. It should rely somehow on topology. So, yeah, sure, tic-tac-toe, you play with X's and O's in a grid. Topological games, you play with open sets. You play with points in open sets. You play with combinations of open and closed sets. Who knows? The second extra aspect of topological games that we should be aware of is that they last an infinite number of turns. This is where the infinite part comes from. So you might be wondering, wait, what does that mean? When does the game end? And yeah, the game doesn't end. Chess ends when someone mates your king. Tic-tac-toe ends when someone gets 3 in a row. Topological games just don't end. This is why I titled this series, the game you can win but cannot play. Because they have, like all these games, they have winning strategies, but if you were to actually play them, you'd have to have 1 turn for every natural number, which obviously you can't actually do in playing against someone, so you can't play the game. Alright, so you might be still confused. So if the game doesn't end, well, how do you determine who wins? Because usually it's at the end of the game when you determine who wins the game. And, well, you just have to shift your thinking, I think. So, instead of thinking about, within a finite amount of time they do blah, 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 and then, after it's all done, blah, blah, blah happens, and we determine the winner, we instead say, okay, player 1 and player 2 each have their own strategy. And that strategy we may think of as sort of a function that maps, all the previous plays to the play that they're about to make. And on a given turn n, we can determine what a player's move is on that turn by sort of just consecutively applying that strategy to the previous board states. And in doing so, we get a sequence of numbers. We get a sequence of board states, effectively. And really, when we determine who wins, we determine if that sequence has a particular property. So, for a finite game, that property might be, is the last element of the sequence one in which the king is checkmated? Or, over the course of all of these terms, and the points that players gain in all of these moves, who has more points. And topological games are just the exact same way. It's just that the sequence, whose property you're trying to determine, it happens to be an infinite sequence. Alright, now we can finally get on to what we've all been waiting for. How to actually play the Banach-Mazur game. How to actually play a topological game. So, to play this game, you'll need three things. You will first need a topological space, y. Next, you will need some subset of that space, x. And finally, you'll need script w, a class of subsets in y, such that the following two conditions hold. Firstly, if you have some any old set w inside that's a member of this class, script w, then within it, there should be, that is contained within it, this is a subset now, there should be some set y prime that is an open set in y. Similarly, within every y prime that is a non-empty open set in y, under the topology of y, we should be able to find a w in script w within it. So the sets in script w and the open sets in y have to be nested within each other like this. So once you have these three things that you need, you can play mbxy script w, which is how Telgársky designates this sort of original. It's not technically the exact version of the Banach-Mazur game that Mazur actually wrote in the Scottish book. It's a generalization by a guy named Oxtoby, but it's close enough. Now, this is how the Banach-Mazur game is designated. So, here's how you play. Player 1 starts, come over here. Player 1 starts by choosing some set W1 that's in this class script W. So this is move 1, W1. Then, player 2 chooses some set W2 for turn 2 that is a subset of W1. Then player 2 chooses, some W3, that's a subset of W2. And player 2 chooses a W4 for turn 4. And then we have then we can move on to turn 5 and turn 6, and so on. Infinitely, of course, because this game is an infinite game that takes infinitely many turns. So, when all is said and done, when all aleph naught or omega, or however you want to say it, turns have passed, player 1 wins if and only if, oh shoot, I wrote that wrong. If and only if the intersection of x, or set x up here, with the infinite intersection of all wn is not empty. So, maybe we have our original set, x, and it's just a whole bunch of points scattered around here. Then, whatever set we get when we take this infinite intersection, there should be some point of x that is in there. And if there's no point of x that's in there, if in taking all these, increasingly decreasing wn's and taking their infinite intersections, if we do that and we get, a set that is disjoint with x, that doesn't contain any points with x, then this intersection is the empty set, and player 2 wins. So this is all very abstract at this point, so I think that we should actually try and play a round of this. Of course, not a full round, because that would take us forever, but maybe we'll watch some people, play a few rounds and see what sort of strategies they use to try and win this weird game. Alright, so let's get right into playing some example games, or some example finite segments of games, of this weird and wacky and topologically twisty Banach-Mazur game. And who better to demonstrate the weirdness, the wackiness, and the topological twistiness of this infinite game than two characters who are very familiar with games that don't make any sense. Namely, Calvin and Hobbes. Because as we know, the only rule of Calvin ball is that if the intersection of all the sets W sub n intersects the set X, then Calvin wins. So let's start off with the version of the Banach-Mazur game where our topological space is just the real number line, the set of real numbers R with a standard topology, wherein our subset that Calvin's trying to target and Hobbes is trying to avoid is Z, the set of integers, so, every positive and negative whole number, so 0, 1, minus 1, 2, minus 2, 3, minus 3, etc. And the class of subsets script W that we're going to be looking at is the set of all closed intervals. Now, why are we choosing this class of subsets, you might ask? Well, the answer is that there's this really handy theorem called Cantor's intersection theorem. And Cantor's intersection theorem says that if you have a whole bunch of, nested closed intervals, and, in R, and you can incidentally generalize this to any old complete metric space, that's a topological space where A, you have a sort of distance defined on your points, and B, every Cauchy sequence, every sequence of numbers that gets, closer and closer together, converges. It sort of, has a limit at a specific point. Anyway, if you have, progressively getting smaller and smaller, nested, closed subsets of a complete metric space, or closed intervals of R, then the infinite intersection of them is guaranteed to be non-empty. And that's, as you can imagine, very useful in this game, because it makes it that the end game, so to speak, doesn't get boring, instead of just being like, oh, the intersection of all these sets is empty, I guess. Alright, I guess Hobbes wins by default. Yes, and by the way, if you weren't already clear, Calvin's player, I used the opposite colors last time. Calvin is player 1, and Hobbes is player 2. Yeah, so instead of being like that, there's actually points in the set, usually 1 point, in fact. And we can say, is that point in this set? Well, let's see. Ooh, tension. Anyway, it just makes the game more interesting, is what I'm trying to say. Anyway, with that out of the way, let's get right into the game. So, let's say that Calvin here, me, I'm Calvin, decides to start off the game with the good old closed interval from minus 3 to 12. Alright, a reasonable start. Now Hobbes chooses a subinterval of that. A subset of that is also a closed interval. So maybe Hobbes, in response, is going to choose the set that is the closed interval from minus 2 to 8. Minus 2 to 8. Ooh, take that, Calvin. Alright, so now turn 3. Calvin's going to respond with minus 1 to 5. Ooh, it's getting tense. Now Hobbes is responding. And what's Hobbes' move? And what is Hobbes's move going to be? Well, it's going to be a further subset from -1 to 2. Oh, tension, tension. It's getting narrower and narrower. Now Calvin is going to go from -0.5 to 1.5. And now Hobbes just decides, hey, I'm done toying with you, Murg. This is how they talk, of course, by the way. And Hobbes just goes, alright, new close set. It's 0.25 to 0.75. And now, the game continues an infinite number of turns. Maybe Calvin continues and goes, okay, about 1/3, 2/3. That's his next move, but at this point, it's basically a foregone conclusion that Hobbes has won, right? Because if we take the infinite intersection of all these sets, it's going to have to be a subset of this interval right here that Hobbes just made, from 0.25, from 1/4, to 0.75, to 3/4. It's going to have to be, some subset of this interval here, or a point on this interval here, and, well, to put it simply, there aren't any integers in this subset. So this means that our final infinite intersection of all these sets here, that's not going to have any integers in it. So Hobbes wins. And in fact, Hobbes could have won much earlier. Hobbes could have won on his very first turn, in fact. He could have de facto won just by, do that. He could have done that on his first turn. He was just kind of toying with Calvin for these first couple turns. Just to pretend like Calvin had a chance. But in fact, he didn't. Alright, so that was a pretty quick game. So let's try another one. So now, let's say that instead of our target set being the set of integers, it is now the open interval from -2 to 6. So now the infinite intersection has to be in this open interval. It has to be a subset of that open interval. So now, let's start the game. Calvin makes the first move. I choose the closed interval from 1 to 5. And Calvin's won now, because no matter what Hobbes does, maybe 0, 3, I don't know, and then no matter what both players do, for the infinite number of turns that are remaining, that intersection, A, it's going to be non-empty thanks to Cantor's intersection theorem, and B, it's going to be in this interval here, because it's in the intersection of this interval with all the other intervals, and this interval is, of course, a subset of this interval, so, whatever this infinite intersection ends up being of all these sets, well, it has to be contained in this set, and thus that set. So this intersection here is non-empty. So Calvin wins. Yeah, I win, I'm going, yeah. Alright, so now let's say that we want a game of the Banach-Mazur game that doesn't, de facto end in less than 2 turns. So for that, let's have a bit of a fancier subset of R as our target set. Let's have the set of rational numbers as the subset of our topological space that we want. And for simplicity's sake, we'll say that, we're just going to talk about the strictly positive rational numbers and the strictly positive real numbers in this case. So it has to be, greater than 0, strictly greater than 0, no negatives, no 0 allowed here. And this is going to be a little trickier, because now instead of just going, yeah, I go into an interval that doesn't contain any of this, or I go into an interval and all of the interval is this, like we had in the previous 2 games, the set of rational numbers is kind of spread throughout the reals. They're kind of everywhere in the reals, but also kind of not everywhere, if you catch my drift. Whoa, dude. Anyway, so this is actually going to be a pretty fun round. So, Calvin will start. And let's say Calvin starts with a good old closed interval from 1/10 to 10. Alright. Now, Hobbes has a response. Hobbes is like, I think I'm gonna go from 1/10 to 9/10. Ooh, how diabolical. But Calvin has a response. And what is that response? Well, maybe that response is something along the lines of the closed interval from 0.15 to 0.85. Now Hobbes looks at that, and Hobbes decides, how about the closed interval from 0.15 to 0.45? Alright, interesting. So, perhaps Calvin looks at this and decides, alright, let's kind of feel Hobbes out here. Let's go with 0.16, 0.44, shrinking it a little. And now Hobbes decides, ooh, you know what? I think that's a nice interval right there. That's a good interval. Let's keep it. My subinterval of the interval you just played, just going to be the same interval. Technically, it's a subinterval. And now Calvin's really thinking, the wheels are cogitating in his brain. And he's deciding, okay, in response to your utterly diabolical move, I'm going to go 0.2 to 0.4, from 1/5 to 2/5. Now Hobbes says, alright, I'm going to go from 0.2 to, I'm feeling this on pi day, so let's say pi over 10. So, 0.31415926589793238462643, etc., etc. I mean, I've been just doing, decimals and fractions here, but, these are closed intervals on the real line. They can be any real numbers. And now Calvin says, okay, let's be less confusing and just say 0.2 to 0.3. Hobbes decides, okay, let's keep it that way. That's another one that I like. I'm keeping that interval like it is. Alright, so, we have quite a few turns of this game played out by now. And, of course, Calvin and Hobbes, they're going to keep on playing this game, ad infinitum. But it's not immediately obvious at this point who's going to win. Do you have any idea who's going to win at this point? Would you believe me if I told you that it was going to be Hobbes? Okay, maybe you do, maybe you don't. But let me explain the very clever strategy that Hobbes is engaging in right now. So you see, the set of rational numbers has a very particular quality that mathematicians call countability. And if you have an infinite set, it's a set that, goes on for infinity, there's an infinite number of rational numbers, there's an infinite number of real numbers, then that infinite set is called a countable set if you can put them in an infinite sequence, if you can make each one correspond to a natural number. For a given natural number, here's a corresponding member of the set, and for any member of the set, I can tell you the natural number corresponding to it. So, the rational numbers, as it happens, are one of these the rational numbers are one of these countable sets. And that might seem a bit weird to me because they're kind of everywhere throughout the line. How can you make one for every single natural number? Well, it's quite simple. Every natural number can be represented as P over Q, where P and Q are integers. And since we're only dealing with positive rationals here, we can say that P and Q are both natural numbers. So let's first list out all of the rational numbers where P plus Q equals 2. We could also go, 0 over 2 and 2 over 0 here, but we don't really worry about that because we're only dealing with positive rational numbers and also dividing by 0 in the real number line. No. Alright, now let's do all the ones where P plus Q equals 3. Okay, we list all these out. 1 over 2, 2 over 1. Alright, now let's list out all the rational numbers whose where the sum of the numerator and the denominator equals 4. Sorry, equals, 4. Blah. Yes, they equal 4. I didn't misspeak. I thought I misspoke, but I didn't misspeak. Where the sum equals 4. So that's 1 over 3, 2 over 2, except wait a minute, we already have 2 over 2, because we already have the number 1 over there, so let's just skip over that. Then we have 3 over 1, and then 4 over 0, which, again, whatever, you can't divide by 0 in this number system. Alright, now the ones where the sum equals 5. 1 over 4, 2 over 3, 3 over 2, 4 over 1. And we keep on going in this vein, and eventually, every rational number will end up being listed in this list. So Hobbes' sneaky strategy, because remember, just as this here is a sequence, it's, an infinite list, it is, you can think of it as, any given natural number corresponds to a rational number, and every rational number is somewhere in here, has some natural number corresponding to it. Well, same deal with the turns that Hobbes takes in this infinite game. So on turn 1, Hobbes' strategy is to specifically choose an interval that avoids rational number 1, that is, 1. Then on his second turn, Hobbes' strategy is to choose an interval that avoids rational number 2, 1/2. Then, on turn 3, Hobbes' strategy is to pick an interval that does not contain the rational number 3, that is, 2. And of course, the interval he was given didn't have 2 in it already, so Hobbes could just kind of hang back and keep it the same, just to be a little smug. Alright, turn number 4. Well, rational number 4 is 1/3. So let's pick an interval that doesn't contain 1/3. Alright, turn number 5. Rational number 5 is 3. So let's pick an interval that does not contain 3. Of course, this interval already doesn't contain 3, so we're golden. We can just keep it the same. Turn 6. Sixth rational number in this listing is 1/4. And well, we're going to make sure that this new interval doesn't contain 1/4. So now, when we go to take the infinite intersection of all of these sets, and Calvin is hoping, to the dear God above, that, this intersection does contain at least one positive rational number. Well, Hobbes has made sure that it can't, because for any positive rational number, P over Q, that Calvin is hoping might be in this intersection, if P over Q is in this listing, the nth rational number, then on turn n, Hobbes already made sure that there's going to be an interval here that doesn't contain that number, and thus the infinite intersection does not contain that number, and thus the set of positive rationals intersected with the infinite intersection of, all these intervals, is equal to the empty set, and Hobbes wins. Alright, so now that we've seen a couple example games of the Banach-Mazur game, let's talk a little bit about the general strategy for the game. How you can try and win at the game regardless of, whatever subset and topological space and class of subsets you happen to be working with. But to do that, we're going to need a couple more definitions, a couple more topological definitions, and these will be new to you even if you have taken Ziegelmeyer's class, so pay attention. First, we say that set A is dense in a space X if every non-empty open set in X intersects A, that is, their intersection between that open set and A is non-empty, that is, that open set contains some point that is in A. Another way to say this is if the closure of A is in X. So, the classic example of a set that is dense in the real numbers is the rational numbers. Because if we have any old, open set of real numbers, maybe it's the open interval from pi to pi plus 0.1, 3.1415 blah blah blah, 3.2415 blah blah blah, then in this interval, no matter how small it is, we can always find some rational number, perhaps 3.2. However, contrawise, the set A is nowhere dense in X. If every non-empty open set in X, which we may call U, contains some sort of subset that's also open and non-empty, V, and that V does not intersect A. V and A are disjoint, they share no points. And some other way to think about this is if the interior of the closure of A is empty. So maybe that kind of means you can think of it like, oh, it's like the boundary, but like it's a part of the boundary. Like there's some set where A is a part of the boundary of that set. Or maybe you can think of it as its complement has as a subset at some point an open dense set in X. And nothing importance of this open here, because the complement of Q, the set of irrational numbers, is also a dense set in X. However, it contains no open dense subsets, so Q is not nowhere dense. You can't be both dense and nowhere dense. Just because you're not dense doesn't necessarily mean that you're nowhere dense. So a good example of a nowhere dense set in R is just the set of integers, because, if we have our integers, they're all discrete, separated from each other like that. Then, if we have some open set in R, well, we can always find a subset. Boop, boop. So here's our U, and here's our V. Some subset that is disjoint from the set of integers, that does not contain any integer. Now, here is a little bit of a trickier definition, meager, also known as being of the first category. So A is meager, or of the first category, in X, if it can be written as the countable union of nowhere dense sets in X. So, for instance, Q is meager in R, because, as we have shown earlier, Q is itself a countable set, and each, single point set in R is nowhere dense, so if we take the countable union of, the set, 1, and union that with the set of 1/2, and union that with the set of 2, and union that with the set of 1/3, and union that with the set of 3, and so on, we end up with a countable union of nowhere dense sets. And remember, it has to be countable. R isn't meager, because you have to have an uncountable union there. But in any case, it's a countable union, so it's a countable union of these nowhere dense sets, so Q is meager. And if, this isn't the case, then we say that A is non-meager or of the second category. Finally, we say that a set is co-meager, sometimes also called residual, in X, if its complement is meager in X. So, naturally, Q, that's a meager set, so if we take the set of all irrational numbers in maybe the interval 0 to 1, then that's going to be co-meager in the interval from 0 to 1. Let's get down to business now. Here's the strategy. Here's how you win at the Banach-Mazur game, no matter what target set, no matter what topological space, no matter what class W you start with. If you're player 2, then you have a winning strategy whenever X is meager in Y. If you remember, X being meager in Y, that means it's kind of small in Y, in the sense that we can create a sequence, X sub n, of nowhere dense sets in Y, x1, x2, x3, off forever, whose infinite union is x. Every element of x is in at least one of the sets x sub n. So we have that in our brain now, and let's say it's our nth turn, turn 2n total. What player 1 just played was the set w sub 2n minus 1. That was their nth turn, the 2n minus 1th turn total. What do? Well, we start by saying, okay, this is obviously a set in script w, and script w has the property that every set in it has a subset that is an open set, a non-empty open set, in our topological space Y. So let Y prime be some non-empty open subset of w sub 2n minus 1. Now, we're on our nth turn, and n is a natural number. What else is indexed by the natural numbers? These guys, our sequence of nowhere dense sets. So let's look at the nowhere dense set x sub n for our particular n. Since this set is nowhere dense, and y prime is a non-empty open subset of y, we know that y prime has to have a non-empty open subset of itself, namely y sub n, that's what we're going to be calling it, that does not intersect x sub n, such that they share no points, such that their intersection is empty. So now we have y sub n. All that remains to do is to say, well, script w, the set of sets that we can choose for our moves, it possesses this property wherein every open set, every open non-empty set, keep having to say non-empty, blah, in Y, has to have as a subset some element of script w. So our move, our w sub 2n, is going to be some subset of this non-empty open set y sub n that is in script w. And if we do this, then, much as Hobbes very sneakily managed to construct a situation where the nth rational number, when enumerated in that way, was simply ignored, was removed, was not found in his nth play, we have created a scenario where any given x in the target set is going to be in one of these sets x sub n. And if it's in, a specific x sub n, well, x sub n does not intersect w sub 2n. After all, w sub 2n is a subset of y sub n, and y sub n and x sub n are disjoint themselves. So, if x is not in a particular w sub 2n, it can't be in the intersection of all the w sub n's. And thus, it cannot be in this set, and as this logic applies for every element of x, we have successfully constructed a whole bunch of w sub 2n's. We've made a whole bunch of plays that make this thing completely disjoint from the target set x, just as we desired. Alright, so that's reasonable, okay? It's just a sort of extension of what Hobbes did. Hobbes' choice of nowhere dense sets to represent Q was just, singleton points, basically, that were fractions. But what if we are player 1? Well, in that case, we can do something that combinatorial game theorists like to call strategy stealing. Perhaps it's best explained with a simpler example. Do you remember the game of Nim that I talked about in part 2 of this series? The game wherein you have a whole bunch of doodads. If you take this doodad, you win the last one. And on each turn, you can either take 1 or 2 doodads. So, in this case, player 2 has a winning strategy. The winning strategy is to always leave player 1 with a multiple of 3 doodads. So you go So if player 1 takes 1, player 2 takes 2. If player 2 takes 2, player 1 takes 1. And so on until you get to the point where, you get to just 3. Player 1 takes this, you take 2. Player 1 takes 2. You take the last one. However, if we subtly change the starting board to look like this, then suddenly it's player 1 who has the upper hand. Because what player 1 can do is make a play such that now the board is identical to 1, wherein player 2 would win, except now player 2's going first, effectively. Player 2's the first one to touch this board state. So now player 1's actually the one who's going to win, because player 1's going second on the game that the second player always wins. If player 2 does this, player 1 does this. If player 2 does this, player 1 does this. And then you get to this point, if player 2 does this, player 1 can do, to this, and boom. Player 1 stole the strategy of player 2. Because player 1 got the game into a position where player 2 would normally have a winning strategy, except player 2 is effectively player 1. I maybe explained that a little poorly, but hopefully you got the general idea. Now, in a very similar way, player 1 has a winning strategy in the Banach-Mazur game when x is comeager. Remember, that means its complement is meager, and a non-empty open subset y1 in y. So, much as in the subtraction game, player 1's first move was sneakily calculated to make sure that the game was in a position that would be a winning position for the person who plays second normally. In the Banach-Mazur game, player 1's first move is to choose a w1 in this open subset y1. W1, of course, being an element of script w, and you can find a script w in any non-empty open subset of y. From that point, you're just playing this game, where this is, of course, a meager set in this topological space, because x is comeager in y sub 1, and this is its complement in a subset of y sub 1, in a subspace of y sub 1, I should say. So this set is meager. And so, this is a winning game for player 2, except that now player 2 is going first in this game. So, player 1 gets to use the strategy that player 2 uses when x is meager. So, for instance, maybe we have, this is our x and this is our y. Player 1's first move is, of course, to get the game in a position like this, and then you can just use Hobbes' strategy, avoiding all the q's, because then the infinite intersection of all these sets is going to be not in q, which is now what player 1 wants. But now we run into a small problem. See, if x is comeager, if it is the complement of a meager set, then, as we discussed, player 1 can use player 2's strategy to avoid the meager set, and get it so that the intersection of the meager set with the intersection of all the sets that were played is empty. But that's technically not player 1's win condition in this case. Their win condition is that x, the complement of the meager set, intersected with the intersection of all the things that were played is non-empty. Now, this is a very subtle difference that doesn't come up most of the time, except when this ends up being empty. Because if this is empty, then player 2 automatically wins, no matter what x is. Even if this doesn't contain any points in this meager set, it doesn't contain any points in the complement of the meager set either, so player 1 doesn't win. So the strategy stealing strategy sometimes doesn't work, which is a bit frustrating, but luckily there's a quick little patch we can do. We just mandate that Y be a complete metric space, because if you remember, the Cantor intersection theorem makes it certain that these progressively nested subsets that we're choosing will have a non-empty infinite intersection. Yay! Player 1 can win after all. Now, there are two final notes that I would like to make about these strategies. First of all, we have shown that, provided Y is a metric space, player 1 wins when this is the case, when X is co-meager in a non-empty open subset Y1 in Y. And we've shown that on any old topological space, player 2's winning strategy is enabled when X is meager in Y. You might be wondering, though, does player 2 have a winning strategy on any other subsets of Y? Does player 1 have a winning strategy on any other subsets of Y? Provided, of course, that Y is a complete metric space. This was the question that Mazur originally posed to the Lviv school of mathematicians when he first formulated the problem in the Scottish book. Mazur had found these strategies, but he wasn't sure if there were other ones that might exist. What Banach did, what won him the bottle of wine, was to show that these are indeed if and only if statements, so to speak. That player 2 only has a winning strat in this scenario, provided Y is a complete metric space, and player 2 only has a winning strategy in this scenario. Now, given that, you might notice something a little funny here, which is that these aren't exactly opposites of each other, these two statements. It's not like player 2 has a winning strategy when X is meager in Y, and player 1 has a winning strategy when X isn't meager in Y. No, it's instead that player 2 has a winning strategy when X is meager in Y, and player 1 has a winning strategy with this other weird condition about co-meagerness in a non-empty open subset Y1 in Y. So does that mean that there are situations where neither player 1 nor player 2 have a winning strat? And the answer is yes. There are situations like that. There are sets where this game is not determined. And this is a very strange concept for multiple reasons. For one thing, if you have a finite game that satisfies all the things I talked about in part 2, being deterministic and turn-based and all that, then there's no such thing as an undetermined finite game of perfect information. Like, in the subtraction game, player 1 or player 2 has a winning strategy no matter what the situation is. Even something like chess, it's very hard to tell what the precise winning strategy for players 1 and 2 are, such that one of them always wins, but one does exist. It has to exist. But not in the Banach-Mazur game. You can construct a set where neither player 1 nor player 2 has a winning strategy. Player 2 does not have a way to win no matter what player 1 does. Player 1 does not have a way to win no matter what player 2 does. And the other reason why that's a very weird thing is that the sets X where the game isn't determined if we're taking y to be the real numbers, well, they're very weird sets. One of them is called the Bernstein set. And it's something where to construct it, you have to take this thing called the axiom of choice, which is you have to be able to just randomly take points from infinite sets without any selection function. It's sort of it's a weighty concept in set theory, but suffice to say, it makes it very hard to actually create an example of the set that you can play on. Because again, this is a game that you can win, but cannot play, except for the times when you can't win it, even if you're the other player.